Hello everyone, today I'd like to talk about the periodicity and boundedness of the absolute function recurrence relation by using graphic method. The definition of the absolute function recurrence relation is as follows, where C is a constant. In this section, we will discuss positive C. We'll discuss three cases: C equals to 1, C lies between 0 and 1, and C is larger than 1. When C equals to 1, the recurrence relation has the period 9, and the proof is attached in the project, so I will not show this in the presentation, since it's more like a tedious work. Just now I mentioned the graphic method. So what's the graphic method? The sequence can be written as follows, and we can visualize the changing trend of the sequence, and that's exactly what the graphic method is. Also, how to interpret each graph is very important. To see if the sequence is bounded, we will check if the graph has an upper bound and lower bound. To see if the sequence is periodic, we will check if the graph has repetitive shapes. Also note that in the following graphs, x equals to a sub 0, y equals to a sub 1, both of them are initial values. Now we step into a case that C lies between 0 and 1. At the very beginning, we don't know where to get started, so we randomly choose initial values 5, 7, 99, and 0.1, and the parameter C equals to 0.5. Surprisingly, both of these two graphs shows a periodic pattern, while the initial values of these two graphs are very different. So I wonder if it is a coincidence or not, and our guess is if we choose another pair of initial values, the pattern of the graph might also be the same or similar. Another observation is that even though these two graphs looks like periodic, but in fact, after testing each value, they are not periodic. So here we introduce a term called quasi-periodic, which means the pattern of the graph is seemingly periodic, but actually is not periodic. To validate my guess, I further test more cases, like initial values minus 5 and 7, initial values 5 and minus 7, initial values minus 5 and minus 7. Surprisingly, all the three graphs shows a very similar pattern as the previous two graphs. I also add an extreme case that initial values are equal to each other. That is, x equals to 5, y equals to 5. And the shape of this graph is still very similar to the previous 5 graphs. So now we can come to our first summary. That is, the parameter C dominates the shape of the graph, while the initial values have very little impact on the shape of the graph. And this is very important to our next exploration, that is how the shape changes as C goes from 0 to 1. Now we choose to select a sub 0 equals to 5, a sub 1 equals to 7, and we don't have to worry about these initial values' impact on the shape of the graph. To clearly compare each graph with distinct C value, we choose to set each graph to 5 peaks. And in the first picture, there are 5 peaks in total. This is the first peak, this is the second one, and so on and so forth. Also, to better compare each graph, we need to pay attention to another value on the bottom right corner, that is ultimate position n. In the first graph, when equals to 0.1, we need 8,000 iterations to get 5 peaks. When C equals to 0.2, we need 2,000 iterations to get 5 peaks. And the third graph is 400 iterations, the fourth graph is 200 iterations, and this one is 140 iterations, and this one is 80 iterations. From the above 6 graphs, we also observe that the width of each quasi-periodicity narrows as C becomes larger. Now we come to our second summary. Each graph above seems to be periodic as c goes from 0 to 1. However, after testing each value on the graph, the sequence is not periodic. So we have our conjecture that when c lies between 0 and 1, the recurrence relation is bounded. Particularly, when c equals to 1, the sequence is periodic with the period line. What happens to c larger than 1? The first pair of value is 1.01 and 1. Both of the graphs shows an incredibly elegant pattern, and the first sequence is quasi-periodic. And it's not surprised to see such an elegant graph, since the number 1.01 is pretty close to the number 1, and these two graphs should show a very similar pattern, that is, like the periodic. Another pair of values is 1.05 and 1.09. These two graphs are very chaotic, and seems that there are no rules in it. But anyway, these two graphs are bounded. This is a very interesting example. When c equals to 1.09 and 7, the sequence still bounded. Well, after adding 0.0003 to the value c, then the sequence becomes unbounded. There's a very little gap between these two values, but these two graphs shows a very big difference. So what happens to the very small gap? Until now, we are not very clear about this small gap. So if you have any comments or ideas about this gap, you can share it with us after the presentation. Also, in the second graph, when c equals to 1.1, the sequence is unbounded. So I wonder if the value 1.1 is the boundary value between the boundedness and unboundedness. I choose to test more cases like 1.2, 1.3, 1.4, 1.5. And the graphs sometimes seem to be unbounded, sometimes being quasi-periodic, so it's kind of a mess, and we are not quite clear about the property of a sequence when c lies between 1.1 and 2. Now, when c equals to 2, we can see a very straight line, and the line will extend to infinity when n goes into infinity. So in this case, the sequence is unbounded. Also, when c is larger than 2, the sequence is unbounded as well. The reason is as follows: since the inequality holds, and also the sequence is unbounded when c equals to 2, then the sequence is unbounded when c is larger than 2. Ultimately, I want to make an overall conclusion about the periodicity and boundedness for the following two recurrence relation forms. For alternating recurrence relation, when the pair value bc equals to the following values, the sequence is periodic and thus bounded. For other integral cases, the sequence is not periodic. For absolute function recurrence relation, when c equals to 1, the sequence is periodic. When c is larger than or equal to 2, the sequence is unbounded and thus not periodic. For other cases, we have conjectures for c lies between 0 and 1, and the interval 1.1 to 2 is a mystery.